In this video, we are going to be looking at some multiple linear regression aspects in R. So what we're going to start with is actually generating a random sample of variables such that we can kind of build a multiple regression based on, in this case, just two predictors. So what we're going to do, I'll go ahead and set a seed in case you want to just reproduce my results. I'm going to set a sample size, so I'm going to collect 100 different observations. Each of these 100 observations is going to have two predictor values as well as a response value as well, right? So it's not 100, numbers, but it's 100 data points with each data point having three values, two of them being predictor values, one of them being a response value. I'm also going to set p equals to 3 because I'm going to use that later to represent the number of parameters in my model. So even though there's only two predictors, there are three parameters because the intercept is going to be a third parameter that I'm estimating with my model. This information right here is just going to set the parameters I'll be using. So I'm going to build this relationship such that the intercept is 5. The slope coefficient for the first predictor is -2. For the second, it's going to be 6. And sigma is going to be 4 to represent the amount of residual variation that's still left in the model after fitting. So again, this is not representing a perfect relationship between these variables, but kind of an underlying relationship with a certain amount of unexplained variability as well. So I'll go ahead and run that. And now I'm going to simulate these values. So I'm going to, these are probably going to make the most sense, right? So I'm going to simulate some random x values. It doesn't really matter what they are since they're just going to be used for prediction. So I'm just going to do sequences of 1 to 10 and kind of split them out equally from 1 to 10 here. I'm also going to make a sequence of x sub zeros to kind of represent this intercept. So this is going to be helpful when I make my X matrix later. When we're kind of demonstrating some stuff with how beta hat is calculated using some of the matrix operations, we'll want this in our X matrix here. That said, we don't necessarily need this to run our linear model. So if I want to do a linear model of Y built upon x1 and x2, then this is all I would need. So this is just more to demonstrate the matrix operations later. All right, so I'm going to also bind those together in an X matrix, which we'll come back to later. And then next, we're going to simulate kind of this response variable. So first, I'm going to simulate epsilon. So these are going to be kind of my random errors, my residuals for each of these 100 observations. So it's going to be normally distributed with a mean of 0 and a standard deviation of what I set for sigma earlier. And then now I'm going to kind of create this response variable to follow this relationship with the residual values that I kind of set over here. So if I go to epsilon here, these are kind of this is my random noise. So this is going to be added to my underlying model to kind of simulate a more realistic response situation. And then I'm going to save x1, x2, and y under a data frame. So this way I can kind of call in it when I'm building a model and different things like that. So I think it's always fun to kind of visualize our data, and certainly if you were doing a multiple regression where we had 3 or more predictors, that wouldn't really be possible without doing kind of some extra plotting that doesn't quite show us the picture. But if we only have 2 predictors, we can actually make a 3D plot. So this isn't really required coding in the course. It doesn't necessarily need to be something that you should know how to do, or I should just say you won't need to know how to do this. But I'm going to be using a package called Plotly that allows us to kind of make this 3D figure. And I think this is really helpful for kind of seeing this. And I can also kind of navigate around while I do this, which is kind of cool. So I can click on the screen and I can kind of move around and I can see the relationship between my variables. So one thing that you might notice here is that we have x1 and x2 down here, and then y is kind of this vertical axis. And so if you remember from the parameters I set, x1 has a negative correlation, x2 is going to have a positive correlation. So if I go to x1 over here, and I'm going from 2 to 10, you're going to notice in general the slope is going down. If I go over here to x2, the slope is definitely going up. So that information can be kind of helpful. And the other thing I can kind of notice is, in this case, x1 and x2 are completely independent of one another, meaning that that it kind of has this additive relationship where if I go this far over with x1 and this far over with x2, I can pretty well kind of see these individual linear relationships here forming a plane, right? So as we mentioned before, when we're fitting two predictors, it's not really a best fit line anymore. It's actually a best fit plane. And if you keep adding predictors, the thing that we're fitting keeps kind of increasing in dimensionality. So in this case, two predictors gives us kind of a best fit plane here. You can also see kind of this random variation, right? So right here, it's not perfectly in a plane. If I were to reduce sigma to a small value, like maybe if I reduce sigma to 0, then these data points should be pretty much exactly in a plane. So let's go ahead and try that just for fun. I don't necessarily need to run all of this stuff again, but I don't remember which ones I necessarily need. So if I take sigma down to 0, then I do get kind of that perfect relationship. There is no kind of random noise around this relationship. I can also, this might be interesting, let me put sigma back to where it was. Or actually, let me keep it where it is because this will probably make it easier. Let's go ahead and make beta 2 a 0 coefficient. So let's say this second predictor has no underlying relationship with the response variable. And let's go ahead and see what happens when I run this. I actually don't need to run that again. I just realized it's only this right here that I need. And so if this is the case, what we're going to notice here is that we have a relationship with x1, but not with x2. So if I go over here to x1, there is that line you see. However, x2 is just random, right? So like it doesn't matter where on this x2 scale I am, my prediction is still going to be the same. And I left sigma as 0 just to make it really, really easy to see. But if we go ahead and put sigma back for a second, if I put it back at 4, and then run this again, we're still going to see x2 has no relationship, but then the random noise is going to be kind of back in here again, right? So relationship here, no relationship from this dimension, and the random noise aspect exists again. All right, so I'm going to put this back just for sake of moving on here. So let me run this again. Okay. So let's check some matrix operations here. So one thing that we talked about is how there's this matrix C that represents the inverse of transpose x times x. And so if I run that, and then I can generate my beta hat estimate. So this vector of best estimates for beta naught, beta 1, beta 2, for as many betas as I have, is going to be represented by this, which we're just going to call C to make it a little bit easier, times the transpose of x times y. So I'm going to run this, and I'll have my estimates for beta hat show up in this vector of 3 elements. Now, if I check that against the model output, so I'm going to build a model here with y being built from x1 and x2, these coefficients should match what comes out in the summary model. And it looks like they do, where I have 4.28, negative 2.01, 6.0476. So we can just kind of verify the matrix operations are matching what we would see if we ran the LM function here. I can do the same thing with the residual standard deviation estimate. So we know that that y hat should be our x multiplied by our beta hat vector. So I'm going to do that first. And then I'm going to kind of manually, quote unquote manually using R, calculate the standard deviation of the residuals here using the formula that I know it should follow. So kind of my squared residuals divided by n minus p, and these squared residuals are being summed up, and then I take the square root again. So if I kind of calculate this, with all the pieces there, I can compare that to the sigma value I get from the summary model, which should be about the same as what I just calculated there. So again, this calculation should match our summary output. Now let's go ahead and just kind of test the distribution of one of these betas. So as we talked about before, there is this distribution of possible beta hats that we could get for each of the beta coefficients, right? So there exist true betas, there exist these true parameters, and then if we take a random sample from this population, we're going to be estimating what those are. We're going to have some beta hats, and each of our beta hats has a distribution of possibilities that's going to be distributed around the true parameter in a normal distribution shape. So what I'm going to do here is I'm going to simulate taking random samples 10,000 times. So just kind of following this model with some random noise, and then calculating some beta hats each time. And I'm going to save all my beta hat 2s in particular to a vector. So now I have kind of 10,000 randomly generated beta hat 2 values from this model. And so then if I plot these here in a histogram, they should be centered around 6, and they should be in a pretty normally distributed shape by this point if I'm doing samples of 100 each. And obviously there's some variations, so some of my beta hats, my beta hat 2s are a little bit high, some of them are a little bit low, but I know if I'm doing inference that I'm going to get a beta hat that's somewhere in this distribution, and I know about how often it should be in different ranges. So that's where these kind of t distributions come in, is if I know the standard error of my beta hat value, then I can use that to kind of figure out how often I should be within different distances of the true parameter. Now, I'm going to go ahead and make this a little bit more realistic with some real data here, representing, this is some serial data. And what we're going to do here is model the caloric, I'm trying to sound too fancy, the calories in different boxes of cereal based on the sugar count and the carbohydrate count of that cereal. So how well can we model the total calories for a serving of cereal based on the number of grams of sugar in a serving, the number of grams of carbohydrates in that serving. So I'm going to go ahead and just build this model, and I have these two predictors here, and it looks like they're both they both seem to have some linear relationship with calories. I'm actually explaining a fair amount of variability, about 66% of the variability, right? I guess I should go over here. 67% of the variability in caloric intake seems to be explained by knowing sugars and carbohydrate counts. I'm going to go ahead and do Plotly again as well. I have a little bit more this time here, so not just, let me get this all kind of easy to see here. So instead of just running this part, I'm going to run some fancy stuff to put some labels on it, because this is just going to give me like X, Y, and Z, but I want the actual labels of the variables on here. So I'm going to do a little bit of extra work to do that. So I'm going to run this. I'm going to save the template that I use. I just plug in X, Y, and Z to make it easy. So I just kind of define my variables as X, Y, and Z there up front. Okay, and then there it is. So here's my serial data, and I definitely seem to have a relationship here. So if I go around to carbohydrates and cereal, so if I look at the carbohydrates one, I definitely see kind of a linear trend going on here where calories tends to be going up. It's a little bit messy, but there is seemingly a positive linear relationship there. Same thing over here with this is sugars. This one again, pretty messy. It's not quite as, the variance doesn't seem quite as constant as I would like it to be. It might partly be because I don't have I have a relatively small sample, and it's kind of hard to talk about cereals as being a random sample if we just have like all the cereals in a store, right? But I definitely seem to see some trend here between both sugars and carbohydrates in terms of caloric intake. The one thing that I will mention, unlike the simulated data, Sugar and carbohydrates probably has a little bit of a relationship as well. It does look like as sugar goes up, carbohydrates goes down, that those maybe have a slightly negative relationship. It's not a super strong one, but I just kind of want to point that out, is that when our predictors have a little bit of a relationship themselves, we should keep that in mind, and we'll talk about that a little bit more later in the class. But we definitely can see a little bit of a plane here with certainly some random noise mixed in. But I can definitely kind of see that as sugar goes up and carbohydrates goes up, those seem to be the highest count cereals that I have. And then if I go down a little bit, these cereals seem to be a little bit lower. Okay. So I can also just use my comfort commands here. So confidence intervals, I can just use confint to calculate a confidence interval for each of my beta coefficients. So if I just want to do 95% confidence, I should get intervals for beta naught, beta 1, beta 2. So those are kind of helpful. I can also create a confidence interval for the mean of y at any set of predictor values. So notice that in multiple regression, we do have to define all of our predictors when we do this. So we're not just going to be plugging in one value. We have to define, in this case, both what sugars is and what carbohydrates is to make a prediction and confidence interval around what calories is going to be. So make sure that you kind of set that up as data.frame with those two or more variables defined inside. So I can do that here, and I'm going to get a singular interval for the mean of caloric intake when I expect sugar and carbohydrates to be these values here. And then very similarly, we can do a prediction interval with the exact same setup, except that I just changed this to prediction. So this would now give us a prediction about where 95% of the cereals we would expect them to be in terms of their caloric count. So obviously this range is going to be bigger. It's capturing 95% of the possible values, whereas this interval is a 95% confidence interval for a parameter. It's estimating where the mean of y would be. And then lastly, we talked about multidimensional extrapolation. So it's not enough to necessarily know that the values that I'm plugging in fit within the individual range of each of these predictors, but I do also want to check that I do seem to see cereals around this range for both values at the same time. So in this case, carbo equals 10, sugars equals 5. This is reasonably within the range of values that I see. But for example, if I had carbo at, say, 20, 22, and sugar being really high, like maybe above 10, maybe close to 12, 14, 15, this would be possibly some multidimensional extrapolation, because we really don't have data values in this range, even though we do have data values within this range of sugars and this range of carbohydrates. So we do want to be kind of careful that we're picking points that fall within the cluster of data points that we see, not just each solo predictor by themselves falling in that entire range.